Teltron tubes. Teltron tubes, also known as electron tubes or vacuum tubes, are experimental devices used in physics education to study the behavior of electrons in electric and magnetic fields. They consist of a sealed glass envelope containing electrodes and a vacuum, with a small amount of gas for certain experiments. The main components of a Teltron tube include 1. Cathode. The cathode emits electrons when heated through a process called thermionic emission. 2. Anode. The anode attracts the emitted electrons and is usually positively charged. 3. Grid. In some tubes, a grid is placed between the cathode and anode to control the flow of electrons. 4. Deflection plates. These plates are used to apply electric or magnetic fields to the path of the electrons, allowing for visualization of their trajectories. Electron position in inductors. In inductors, which are passive electrical components used to store and release energy in the form of a magnetic field, electrons do not have fixed positions. Instead, they flow through the wire wound around a core, such as a coil or solenoid. When an electric current flows through the inductor, it generates a magnetic field around the coil, according to Ampere's law. The movement of electrons in the wire is influenced by the voltage applied across the inductor. When a voltage is applied, it creates an electric field that exerts a force on the electrons, causing them to move. In a steady-state condition, the electrons flow uniformly through the wire, contributing to the establishment of the magnetic field. Electron acceleration. Electron acceleration occurs when electrons experience a change in velocity. This change in velocity can result from various factors, including the application of an electric field, such as in a vacuum tube, or the presence of a varying magnetic field, as in an inductor. In a vacuum tube, such as a Teltron tube, electrons emitted from the cathode are accelerated towards the positively charged anode due to the potential difference, voltage between them. As the electrons move towards the anode, they gain kinetic energy, leading to an increase in their velocity. In the context of inductors, electron acceleration can occur when the voltage across the inductor changes over time. According to Faraday's law of electromagnetic induction, a changing magnetic field induces an electromotive force, EMF, in a conductor, which causes electrons to accelerate. This acceleration results in a change in the current flowing through the inductor, as the electrons respond to the changing magnetic field. Voltage in inductors. In an inductor, the voltage across its terminals depends on the rate of change of the current flowing through it. According to the voltage-current relationship in inductors, the voltage V_L across an inductor is proportional to the rate of change of the current with respect to time, where L is the inductance of the inductor, measured in Henry's H. This relationship arises from Faraday's law of electromagnetic induction, which states that a changing magnetic field induces a voltage in a conductor. When the current through the inductor changes, the magnetic field around the coil also changes, inducing a voltage across the inductor. This induced voltage opposes the change in current, in accordance with Lenz's law. As a result, inductors resist changes in current flow, causing voltage spikes or drops depending on the direction and rate of change of the current.